guys, Handsome Nerd ASMR back with another video. In this video we're going to be talking about a very important concept in physiology, and that is the Renin-Angiotensin-Aldosterone system, commonly called the RAAS system. So what is it? It in general is a critical hormonal cascade that plays a very crucial role in regulating blood pressure, fluid and electrolyte balance, and systemic vascular resistance. That is why understanding the Renin-Angiotensin-Aldosterone system is essential, especially when you are understanding or trying to understand the cardiovascular physiology, renal function, and pharmacology. So let's dig into the overview of the RAAS system. The Renin-Angiotensin-Aldosterone system is activated in response to the following: decreased renal perfusion pressure, such as in cases of hypotension and hypovolemia. If there is also sympathetic nervous system activation, then the RAAS can be activated. This typically occurs through the stimulation of the beta-1 adrenergic receptor. Also, if there is decreased sodium delivery to the distal tubuli, this is going to trigger the RAAS system once this decreased sodium delivery is sensed by the macula densa cells in the nephron. And so, the overall effect of the RAAS activation is to increase blood volume and systemic vascular resistance, which will then lead to increased blood pressure. So what are the components and steps of the RAAS system? The first step is to release renin, and this happens to be the rate-limiting step for this system. So renin is synthesized and secreted by the juxtaglomerular cells of the afferent arteriole that is found in the kidney. Thus, release of renin is stimulated by the following: the decreased renal perfusion pressure, and this decreased perfusion pressure is sensed by the baroreceptors in the afferent arteriole. If there is decreased sodium chloride delivery to the macula densa in the distal tubuli, or if there is increased sympathetic stimulation through increased stimulation of the beta-1 receptors on the juxtaglomerular cells. So, to understand what renin is, you can consider it as an aspartyl protease that cleaves the angiotensinogen into an angiotensin 1. So renin is, or I guess it's technically an enzyme, and it is necessary for the production of angiotensin 1. And this is represented by this part of the figure, renin being released from the kidney, leading to the production of angiotensin 1. Next, we have angiotensinogen. Now, angiotensinogen is actually produced by the liver, and it is going to circulate in the plasma until it contacts renin. So, remember how we said that renin is technically an enzyme? Well, if that is the case, then angiotensinogen happens to be the substrate for renin, which is then cleaved. So the angiotensinogen is cleaved, leading to the production of angiotensin 1. And angiotensin 1 can be described as an inactive decapeptide. Afterwards, we have another important step, which is the conversion of angiotensin 1 into angiotensin 2. And this will be carried out by the enzyme called the angiotensin converting enzyme, also known as ACE. The location of this conversion occurs primarily on the surface of pulmonary and renal endothelial cells. And the main action is to convert angiotensinogen, or angiotensin 1, into angiotensin 2. And the angiotensin converting enzyme, or ACE, happens to be released from the lungs. And then the production of angiotensin 2 is ultimately production of an active octapeptide. So once we have angiotensin 2 produced, angiotensin 2 can carry out multiple actions. For starters, angiotensin 2 acts via the AT1 receptors, and sometimes to a lesser extent the AT2 receptors. The key physiological effects include the following. Once the angiotensin 2 acts on the AT1 or the AT2 receptors, first there is vasoconstriction, where the arterioles are directly constricted. This is going to lead to increased systemic vascular resistance, thereby leading to increased blood pressure. There is also going to be aldosterone secretion, which is going to, where the aldosterone that is secreted is going to stimulate let me rephrase that. The aldosterone secretion occurs when the zona glomerulosa of the adrenal cortex is stimulated by angiotensin 2, and this leads to increased aldosterone production and secretion. And then the aldosterone will promote the sodium reabsorption, potassium secretion, and H+ ion secretion in the collecting duct of the nephron. This is going to occur through the epithelial sodium channel, sodium potassium ATPase exchanger, and the H+ ATPase pump. The phrase ATPase basically means that the H+ excretion is powered through the consumption of ATP. Likewise, the reabsorption and the secretion of potassium, or the sodium potassium exchange, requires the consumption of ATP. And we can see it over here that aldosterone is necessary for stimulating reabsorption of salt, technically sodium ion, and then water. And so angiotensin 2, interestingly, also stimulates antidiuretic hormone release via the vasopressin. So there is stimulation of the posterior pituitary gland, and that's going to lead to the release of antidiuretic hormone, which then leads to increased water reabsorption in the collecting ducts. And this will occur through the presence of aquaporin 2 channels. And then there's going to be third stimulation, where the angiotensin 2 acts on the hypothalamic osmoreceptors to increase or induce water intake. And then lastly, there's going to be efferent arterial constriction. And so the efferent arterial constriction is going to maintain the GFR, or the glomerular filtration rate, in low perfusion states by preferentially constricting the efferent arterial border afferent. And so the idea behind this is you want to make sure that less blood is escaping from the glomerulus to the peritubular capillaries when there is already low perfusion of blood to the glomerulus. And so constricting the efferent arteriole will essentially trap more blood within the glomerulus, thereby helping to maintain, or at least ensure, that the glomerular filtration rate does not drop significantly. And that is indicated by the figure right here. So now that we know what angiotensin 2 does and its various responsibilities, let's talk about how pharmacology can be utilized to modulate the Renin-Angiotensin-Aldosterone system. So there are some common drug classes to be aware of that target the RAAS system. The first one, and this is very important, we have ACE inhibitors. This is simply going to inhibit the angiotensin converting enzyme, thereby inhibiting conversion of angiotensin 1 to angiotensin 2. And so the key examples of these drugs are lisinopril and enalapril. Pay attention to how these drugs sound at the end, or pay attention to their suffix. The suffix pril and pril. So lisinopril and enalapril. That's how you know that these are ACE inhibitors. We also have ARBs, or angiotensin receptor blockers, also known as AT1 blockers. These drugs will block the angiotensin 2 receptor at the AT1 site to prevent angiotensin 2 from carrying out its main functions. And so those drugs will include losartan, valsartan, candesartan, any drug that ends with artan. So that's how you know it's an angiotensin receptor blocker. We also have aldosterone antagonists, and so these will actually block aldosterone receptors in the distal nephron, thereby preventing aldosterone's function of stimulating sodium reabsorption and potassium secretion. So these drugs include spironolactone and eplerenone. And you can pay attention to the suffix "-one" and "-one" as in spironolactone and eplerenone. And any drug that sounds like that are most likely aldosterone antagonists. Then we have renin inhibitors, which are responsible for directly inhibiting renin. So one classic drug is aliskiren, and aliskiren is simply a renin inhibitor preventing renin from carrying out its function of converting angiotensinogen into angiotensin 1. So you can see there's at least several pharmacologic targets regarding the RAAS system. Let's also discuss briefly the clinical implications of the RAAS system. So the RAAS system, or at least our understanding of it, will help us to understand the pathophysiology of hypertension, heart failure, and renal artery stenosis. It can also help us to understand why ACE inhibitors can cause hyperkalemia and angioedema. At least for the hyperkalemia part, you know that ACE inhibitors ultimately lead to decreased release of aldosterone, thereby preventing more excretion of potassium. So one danger is increased potassium in the blood, so hyperkalemia. And then understanding RAAS can help us to know how efferent arterial constriction helps to maintain GFR in hypovolemic states, which is why ACE inhibitors are classically known to precipitate acute kidney injury in states of hypovolemia or hypoperfusion. So with every system, there's probably going to be feedback regulation. So regarding negative feedback, angiotensin 2 actually inhibits further renin release through the short loop feedback. And then another factors that can suppress renin release are volume expansion or high blood pressure. So be aware of these factors that can contribute to the feedback regulation of RAAS. And then let's talk a little bit about pathophysiology behind the RAAS system. First one is called primary this involves an aldosterone secreting adrenal adenoma, so a tumor that leads to increased aldosterone secretion, hence the name hyperaldosteronism. So, increased in aldosterone, what do you think is going to happen? Well, there's going to be decreased renin secretion due to that negative feedback, and the clinical presentation will lead to hypertension because of that increased sodium reabsorption, hypokalemia because of that increased potassium secretion, and metabolic alkalosis because of that increased hydrogen ion or H plus secretion. Another pathophysiology pertinent to RAAS is renal artery stenosis. So, in renal artery stenosis, this typically involves decreased perfusion pressure to the kidney, which is obviously going to trigger further increase of renin, which leads to increased production of angiotensin II, thereby leading to secondary hyperaldosteronism. It is secondary hyperaldosteronism rather than primary hyperaldosteronism because the cause of this hyperaldosteronism is attributed to something other than the very source of the aldosterone. In other words, it's something other than the aldosterone secreting adrenal gland that is responsible for this increased production of aldosterone. So, the clinical presentation of renal artery stenosis will include resistant hypertension and the auscultation of abdominal bruits. And interestingly, heart failure also involves the RAAS system. So, it works with the fact that low cardiac output is going to lead to perceived low perfusion, which is then going to lead to chronic renin-angiotensin-aldosterone system activation. As a result of this is going to contribute to fluid retention, thereby worsening preload and edema. So in summary, we talked a lot about the different elements of the RAAS system. So I want to just go over them one more time using this helpful table that I made. So with renin, you're going to have or come from the juxtaglomerular cells of the kidney. It is going to be stimulated by decreased perfusion, decreased sodium chloride in the distal tubuli, and increased sympathetic nervous system activity through the beta-1-adrenergic receptor that we talked about here earlier. Specifically on juxtaglomerular cells. And its function is going to convert angiotensinogen to angiotensin I. Angiotensinogen is produced in the liver. It comes from it. It can be stimulated by various things. And it's going to act as a substrate for renin. And then renin is going to convert angiotensinogen into angiotensin I. Then we have angiotensin converting enzyme, which comes from the lung or the renal endothelium. And its function is to convert angiotensin I into angiotensin II. And then angiotensin II will then be present in circulation of the serum or the blood. And angiotensin II will lead to increased blood pressure, increased aldosterone, increase in antithyroid hormone, and increased in thirst sensation. And finally, aldosterone, which is stimulated by angiotensin II, is going to come from the adrenal cortex, or at least a part of the cortex that makes aldosterone. And the stimulus for aldosterone secretion is obviously the angiotensin 2 and increased potassium, serum potassium levels. And aldosterone will lead to increased sodium reabsorption and decreased potassium. Increased sodium reabsorption and then decreased levels of potassium in the serum. In other words, there's going to be increased potassium secretion. So, that is basically it regarding the RAAS system. Feel free to comment down below any additional information that is worth mentioning regarding the RAAS system. I hope you enjoyed this ASMR style lecture or tutorial. Let me know if you like more ASMR style physiology videos like this in the future. And until then, I'll see you all next time. Peace out.